A user taps a button to request a ride. In exactly 10 seconds, a global network of moving vehicles, fluctuating prices, and spatial calculus must collapse into a single optimal match. During that brief window, the backend processes up to 500,000 GPS writes every single second, generated by 10 million active users globally. This is a continuous, real-time geospatial optimization engine. The data does not rest quietly in a database table waiting to be queried. In a system design interview, a junior engineer might draw a simple relational database and a location table. Under production load, that architecture melts in minutes. Surviving this scale requires a highly specific set of tools: hierarchical geospatial indexing, stateful stream processing, and graceful degradation. We are going to build this architecture piece by piece. We will start with the spatial grid, move to the ingestion pipeline, optimize the dispatch algorithm, and finally deconstruct the surge pricing engine. To make it work, we have to abandon traditional relational databases entirely and model the world through streaming geometry. The intuitive way to find a driver is to take a rider's GPS coordinates, draw a radius, and calculate the distance to every active driver using the Haversine formula. That creates an ON operation, requiring massive, unsustainable CPU overhead. The industry standard fix is to divide the map into smaller squares, using geohash or quad trees, but squares introduce severe edge effects. A driver and rider just 50 meters apart might be completely missed if separated by a grid boundary. Squares are also geometrically flawed. The distance from the center to a diagonal neighbor is farther than to a horizontal one, distorting proximity queries. Uber bypassed this by engineering H3. They projected the Earth onto an icosahedron, tiling the surface with a uniform grid of hexagons. Hexagons possess a unique mathematical advantage. The center point is exactly the same distance from every single neighboring cell. This uniform geometry allows the system to execute perfect K-ring expansions, searching outward in flawless concentric rings without spatial distortion. Because of the hierarchical design, a street-level hexagon at resolution 9 nests mathematically inside a larger neighborhood-level hexagon at resolution 8. By mapping coordinates to these integers, complex geographic boundaries become instantaneous key-value lookups in a database. H3 solves the spatial scaling problem by transforming complex spatial calculus into flat, lightning-fast integer queries. With the geometric framework in place, we have to handle the physical volume of the network. There are up to 5 million active drivers moving across the platform at any given time. Each driver's app pings its location every 4 seconds. Standard HTTP polling would overwhelm the network, so the apps maintain persistent, bidirectional WebSocket connections. Those WebSockets push 500,000 location updates per second into the backend. Writing that volume to a standard relational database will bring the system down. The ingestion pipeline must be strictly bifurcated. Traffic hits a load balancer and immediately forks into a volatile hot path and a durable cold path. On the hot path, the location service maps the incoming GPS ping to its H3 cell ID and writes it to an in-memory Redis cluster for matching. Simultaneously, the cold path publishes raw pings into Apache Kafka topics partitioned by city, creating an immutable historical log for analytics and machine learning. Decoupling the transient matching state from the heavy persistent storage ensures the real-time routing engines are never starved for compute by downstream analytics workloads. When a user requests a ride, the matching engine identifies their H3 cell and queries Redis for available drivers in that exact area. It does not immediately assign the absolute closest car to the first request. Instead, it accumulates requests over a brief, few-second window to perform batch matching. The engine constructs a bipartite graph, evaluating multiple riders and drivers simultaneously. It calculates the minimum cost perfect match to reduce overall wait time for the group, rather than optimizing for a single user. Optimizing the graph relies on accurate time estimates. The shortest physical distance rarely equals the shortest travel time once you factor in live traffic, turn costs, and one-way streets. To fix this, Uber uses DeepIDA, a transformer-based deep learning model designed to correct baseline routing estimates in under 4 milliseconds. DeepIDA does not simply predict the entire route from scratch. It takes the baseline routing estimate and predicts the residual, the specific variance caused by real-world conditions like time of day and live traffic. Once the ideal match is calculated, the system faces a concurrency threat known as double dispatch. In dense areas, two separate match cycles might try assigning one driver to two different riders. The dispatch service applies distributed locks and optimistic concurrency control. When the driver accepts, the resulting state transition is atomic. The first write wins the trip record, and the second is safely rejected. Finding nearby cars is easy. Ensuring the arrival time is highly accurate and guaranteeing a driver is never double assigned turns a theoretical algorithm into a functional physical trip. The ultimate stress test for this architecture is a massive localized demand spike, like a stadium emptying out after a concert. A common mistake is assuming surge pricing is a synchronous calculation triggered by a ride request. In reality, it is a continuous, asynchronous stream processing pipeline. Supply and demand data flows from Kafka directly into Apache Flink, a distributed stream processing engine. Flink aggregates this data into 5-minute sliding windows. It tracks the volume of requests and available drivers, indexing all of it strictly by their H3 cell IDs. A simple system would divide demand by supply for each hexagon, but isolating the math to a single cell causes chaotic, jagged pricing based on small data pools. To stabilize the market, Flink executes K-ring expansions. It pulls in supply metrics from neighboring hexagons to perform spatial smoothing. This prevents extreme price borders that would encourage drivers to cross the street just to chase a higher multiplier. Every 30 seconds, Flink pushes these calculated multipliers into a low-latency Redis cache. This heat map displayed on the driver's phone shows how those updated multipliers constantly broadcast the exact state of the market. Dynamic pricing operates as a continuous geographic gradient. By blending supply data across the grid, the system smooths price transitions and balances the marketplace as demand fluctuations occur. A senior engineer knows that no matter how resilient the architecture is, components will eventually fail. If the entire Apache Flink surge cluster crashes during a high-traffic window, the system is designed to bypass it entirely. The architecture falls back to a stale cache strategy. Redis continues serving the last known surge multiplier for up to 120 seconds, prioritizing a slightly inaccurate price over a broken checkout flow. If the stream is down for more than 3 minutes, a circuit breaker trips. The system defaults all multipliers to 1.0, ensuring riders are not locked into artificially high prices during a prolonged outage. This architecture is defined by 3 layers. Immutable event streams feeding asynchronous aggregators, which then populate in memory indexes organized by mathematically uniform grids. System design accepts that failure is inevitable. The goal is to manage state boundaries, so even when the backend fractures, the user experience remains uninterrupted.